Good morning, everyone. I'm excited to welcome you to today's presentation. We'll be exploring our syllabus coverage through this PowerPoint, focusing on two key topics, weathering and mass wasting. This is part of the Elimu Hub Kenya 1 series. Over the course of this session, we'll go through the main concepts, understand their significance, and see how they connect to our broader studies. So, let's get started and make this an engaging learning experience. Now, let's move on to Part 4, which focuses on external landform processes. These are the natural forces that shape the Earth's surface from outside the land itself. Think of these processes as the Earth's way of constantly reshaping and renewing its landscape. They include things like weathering, erosion, and transportation of sediments. Weathering breaks down rocks at or near the surface, caused by factors like water, wind, and temperature changes. Erosion then takes over, carrying those broken down materials away, often by water or wind. Transportation is the process of moving these sediments from one place to another, which eventually leads to the formation of new landforms like valleys, deltas, and beaches. These processes are essential because they work together to constantly modify the landscape over time. They connect to the overall theme of how Earth's surface is dynamic and ever-changing, driven by forces beyond just tectonic activity. Understanding these external processes helps us appreciate the natural mechanisms that shape the environment around us. All right, let's take a closer look at weathering. Weathering is essentially the process where rocks break down or decompose right where they are in their original position. It's a mechanical disintegration or sometimes chemical decomposition happening right in place, without the rock being moved somewhere else. When I say in situ, that just means the process occurs without any relocation of the material. It's a static process, so the rock isn't transported or moved around during weathering. This distinction is important because it helps us understand that weathering is about change happening right where the rock sits, which is fundamental to the formation of soil and landscape features. Remember, this process is crucial because it sets the stage for erosion and other geological processes that shape our Earth's surface over time. Now let's take a look at the main agents of weathering. These are the forces that gradually break down rocks and minerals over time. First up is heat. When temperatures fluctuate, especially through processes like heating and cooling, they cause expansion and contraction in rocks. Over time, this stress creates cracks and eventually leads to the breakdown of the material. Next, water plays a huge role. It can seep into tiny cracks and, through processes like freeze-thaw, cause rocks to fragment. Water is also vital because it acts as a transport medium, carrying dissolved substances that can chemically alter minerals in the rocks. Speaking of dissolved substances, these are often acids or other chemicals that react with minerals, weakening the structure. For example, carbonic acid in rainwater reacts with limestone, leading to chemical weathering. Then we have plants and animals. Roots of plants can grow into cracks, exerting pressure and causing rocks to fracture. Animals, like burrowing creatures, disturb the soil and rocks, helping to expose surfaces to further weathering. All these factors work together, gradually shaping and transforming landscapes over time. Understanding these agents helps us appreciate the complex, natural processes that constantly mold our environment. Now let's take a closer look at the causes of weathering, starting with climate. Climate plays a huge role in how rocks break down over time. In cold and dry climates, physical weathering tends to dominate. That's because the lack of moisture and the chilling temperatures cause rocks to fracture and break apart more easily through processes like freeze-thaw action. On the other hand, in warm and wet climates, chemical weathering is much more prevalent. The abundant moisture and heat accelerate chemical reactions, which can dissolve minerals and alter the rock's structure. Frost action, or freeze-thaw cycles, are especially effective where temperatures fluctuate widely. When water seeps into cracks, freezes, expands, and then melts, it gradually pries rocks apart. This process is most active where the temperature swings between above and below freezing, causing repeated expansion and contraction. So, in essence, the climate setting, whether dry or wet, cold or warm, directly influences whether physical or chemical weathering is the dominant process. Understanding these climate effects helps us predict how landscapes evolve over time. Now, let's take a closer look at the world distribution of weathering, specifically on a climatic basis. As you can see from this map, weathering processes vary quite a bit depending on the climate of a region. In tropical areas, for instance, high temperatures and abundant rainfall accelerate chemical weathering significantly. This leads to rapid breakdown of rocks and minerals, which is why tropical soils often have a distinct composition. On the other hand, in arid or desert regions, the lack of moisture means physical weathering dominates. Here, rocks tend to break down more slowly through processes like thermal expansion and contraction, but chemical weathering is much less prominent due to the dry conditions. Temperate regions tend to fall somewhere in between, with moderate rainfall and temperatures supporting a mix of chemical and physical weathering. Understanding this distribution is crucial because it helps us predict soil formation, landscape evolution, and even the types of ecosystems that can thrive in different parts of the world. It ties into the overall theme of how climate influences geological processes, shaping the Earth's surface over time. Now, let's take a quick look at the main categories of weathering. First, we have mechanical or physical weathering. This involves the physical breakdown of rocks without changing their chemical composition. Think of processes like freeze-thaw action, where water seeps into cracks, freezes, expands, and gradually splits the rock apart. Then there's thermal expansion, where temperature changes cause rocks to expand and contract, leading to fracturing over time. These processes physically weaken the rock, making it easier for other forms of weathering to take place. Next, we have chemical weathering. This is all about the chemical alteration of minerals within rocks. For example, when rainwater, which often contains dissolved carbon dioxide, reacts with minerals like feldspar, it forms clay and soluble elements. This process effectively dissolves or decomposes the rock from within. Chemical weathering is especially prominent in warm, moist climates because the reactions happen faster under those conditions, contributing significantly to landscape transformation. Finally, there's biological weathering. This involves living organisms contributing to the breakdown of rocks. Think about plant roots growing into cracks and exerting pressure, or lichens and mosses producing acids that chemically attack the rock surfaces. Even animals burrowing can help expose new rock surfaces to weathering agents. Biological weathering beautifully illustrates how life and the environment are interconnected in shaping our landscapes. Connecting this to our overall theme, understanding these categories helps us grasp how different natural processes work together to gradually wear down rocks and sculpt our environment over time. Each type has its own mechanisms, but they often operate simultaneously, reinforcing each other in the ongoing story of landscape evolution. Now, let's talk about mechanical or physical weathering. This is the process where rocks break down without any chemical changes happening. Essentially, the rocks are just physically breaking into smaller pieces. The key point here is that their chemical composition remains the same, even though their size and shape change. So, unlike chemical weathering, which alters the minerals within the rock, physical weathering simply reduces the rock to a smaller, more manageable form. This process is important because it helps prepare rocks for further breakdown by chemical means later on. It's a fundamental part of the overall weathering process, and understanding it gives us insight into how landscapes are shaped over time. Now, let's take a closer look at the different types of mechanical weathering, which all depend on specific physical processes. First up is changing temperature, or what we call thermal expansion. When rocks are exposed to temperature fluctuations, they expand when it's hot and contract when it cools down. Over time, this repeated expansion and contraction can cause the rock to weaken and eventually break apart. Next, we have pressure release or unloading. Imagine a big, thick rock buried deep underground. When the overlying pressure is removed, say, through erosion, the rock expands or unloads, which causes it to crack and fracture. This process often results in large slabs breaking off, like peeling layers from an onion. Finally, there's frost action, also known as freeze-thaw action. This occurs in environments where temperatures fluctuate around the freezing point. Water seeps into cracks and freezes overnight, expanding as it turns to ice. When it melts again, it leaves behind a larger crack. Repeated freeze-thaw cycles exert pressure on the rock, gradually causing pieces to break off. All these processes, thermal expansion, pressure release, and freeze-thaw, are key to physical weathering because they physically break down rocks without changing their chemical composition. Understanding these helps us see how landscapes are shaped over time through natural forces. Now, let's talk about what causes block disintegration, which is a fascinating process. Essentially, it happens because rocks expand during the day when the temperature rises and then contract at night as it cools down. This repeated cycle of heating and cooling leads to stress within the rock. Over time, these stresses cause the rocks to weaken and eventually break apart. The key point here is the high diurnal temperature range. That's the difference between daytime highs and nighttime lows. Because this range is so significant, it accelerates the disintegration process. It's quite interesting to see how this natural temperature fluctuation actively shapes and breaks down rock formations over time. This process ties into the broader theme of physical weathering, where temperature changes play a crucial role in breaking down geological features. So, in essence, the daily cycle of expansion and contraction is a powerful force in landscape evolution, especially in environments with marked temperature differences. Now, let's take a closer look at how rocks expand and crack over time. When rocks are subjected to different environmental conditions, such as temperature changes or moisture, they tend to expand. This expansion isn't uniform, which leads to stress within the rock. Over time, these stresses cause cracks to form and propagate. The process is gradual but significant, as these cracks can eventually lead to the breakdown of the rock into smaller particles. This mechanism is fundamental in understanding weathering and landscape evolution, as it explains how rocks break apart naturally. Remember, the key concept here is that expansion creates internal stress, which then results in cracking and disintegration. This process ties into the broader theme of how geological materials respond to environmental forces over time. Now, let's move on to slide 12, which highlights an important concept about how rocks respond to stress. When a rock is subjected to internal or external forces, it can start to expand slightly. But what's really interesting is what happens as the stress continues to build. The rock doesn't just stretch uniformly. Instead, it begins to develop tiny cracks and weaknesses. These microfractures grow and spread until the rock can no longer hold together. Eventually, the expansion causes the rock to break apart into smaller blocks. This process is crucial because it explains how larger rocks can fracture into smaller, more manageable pieces under pressure, like during natural weathering or geological activity. Understanding this helps us see the bigger picture of how rocks evolve over time, especially under changing environmental conditions. It's a key piece of the puzzle in grasping the mechanics behind rock deformation and fragmentation, which ties back to the overall theme of rock stability and failure. Now let's talk about granular disintegration. When temperature changes occur, they cause complex strains within the rock mass. This is because different minerals in the rock respond differently to heating and cooling. Some minerals expand more than others, leading to internal stress. Over time, these stresses build up, and when the temperature finally drops or cools down, it causes the rock to shatter. This process is a key way that rocks break down over time, especially in environments with frequent temperature fluctuations. Understanding this helps us see how physical weathering contributes to the overall breakdown of rocks in nature. Now, let's move on to the concept of granular disintegration. This is a process where larger particles break down into smaller, more manageable fragments. It's a key phenomenon in many geological and engineering contexts because it influences the stability and behavior of materials. When particles disintegrate, they change the overall structure, affecting porosity, permeability, and strength. Understanding granular disintegration helps us predict how materials will respond under various conditions, like stress or chemical change. It's particularly important in fields like soil mechanics, sedimentology, and even in the design of foundations and earthworks. So, grasping this process allows us to better anticipate and manage the stability of natural and artificial structures. Remember, this concept ties into the larger theme of material behavior and how microscopic processes impact macroscopic stability. Now, let's take a look at exfoliation, also known as onion weathering. This is a fascinating process where curved layers or plates of rock start to break away from the main rock body. Think of it like peeling an onion. These layers gradually peel off over time. This process mainly happens when the outer rock is subjected to expansion and contraction forces. For example, during hot days, the outer layer expands, and then it contracts when it cools down at night. Over time, these repeated cycles cause the outer layers to weaken and eventually peel away. The key point here is that exfoliation results in these thin, curved sheets breaking off, which can significantly shape the landscape. It's a crucial part of the larger weathering process that helps break down rocks into smaller pieces. And of course, this ties into our overall theme of how natural forces gradually wear down and shape our environment. Understanding exfoliation gives us insight into the physical changes that happen slowly but steadily over geological time. All right, let's talk about exfoliation and onion weathering. These are fascinating processes that help shape our Earth's surface. Exfoliation, also known as onion weathering, mainly occurs in regions with large temperature fluctuations. When the surface heats up during the day, it expands and then contracts at night as it cools down. Over time, this repeated expansion and contraction cause layers of rock to peel off in a manner similar to layers of an onion. It's a slow but powerful process that gradually breaks down rocks into smaller pieces. This process is especially common in granite landscapes, where the rocks have a lot of internal cracks and joints. It's interesting because it doesn't rely on chemical changes, but rather physical ones, just the natural stress from temperature differences doing the work. This process contributes to the formation of angular rock fragments, which can then be further broken down by other weathering processes. Overall, exfoliation is a key physical weathering mechanism that helps shape rocky terrains, especially in arid or semi-arid environments. It's a perfect example of how Earth's natural temperature cycles can influence the landscape over time. All right, let's talk about exfoliation, also known as onion weathering, which is a fascinating process in geomorphology. Essentially, exfoliation occurs when large masses of rock peel away in layers, much like the layers of an onion. This typically happens in environments where rocks are subjected to significant temperature variations. During the day, the surface heats up, causing the outer layers to expand, and at night, the temperature drops, leading to contraction. Over time, these repeated cycles create stress within the rock, causing it to fracture and peel off in sheets. This process is particularly common in regions with large diurnal temperature ranges, such as deserts or certain mountainous areas. An important point to remember is that exfoliation is a form of mechanical weathering. It doesn't involve chemical changes, but rather physical breakdown of rocks. Connecting this to the broader theme, exfoliation plays a key role in shaping landscapes and contributes to soil formation as these layers eventually detach and break apart. It's a slow but steady process that highlights how climate and environmental conditions influence geological features. So, understanding onion weathering gives us insight into how rocks evolve and landscapes change over time. Now, let's take a closer look at the exfoliation dome, which is located in Yosemite National Park in California's Sierra Nevada mountains. This geological feature is a fascinating example of how natural processes shape the landscape over millions of years. The dome itself was formed through a process called exfoliation, where layers of rock peel away like the layers of an onion. This happens because of pressure release as the overlying rocks are eroded away, allowing the underlying rock to expand and crack. What's really interesting is that this process creates these smooth, rounded shapes that are quite distinctive and visually striking. It's a perfect illustration of how natural forces like erosion and mechanical weathering work together to sculpt such unique formations. And understanding these processes helps us appreciate the dynamic and ever-changing nature of our planet's surface. So this dome isn't just a beautiful sight. It's a testament to the ongoing geological activity that continuously transforms the landscape around us, reinforcing the theme of Earth's dynamic, ever-evolving geology. Now let's talk about frost weathering, which is a fascinating natural process. When water seeps into tiny cracks in rocks, it may seem harmless at first, but the real magic happens when that water freezes. As it turns into ice, it expands by almost 10%, exerting a lot of pressure on the surrounding rock. This repeated freezing and thawing gradually causes the rock to break apart. Over time, this process produces jagged, angular fragments. It's a prime example of how physical weathering shapes our landscape, especially in colder climates. Understanding frost weathering helps us see how rocks are broken down over time, contributing to soil formation and landscape evolution. It's a key piece of the puzzle in the bigger picture of erosion and landform development. All right, now let's talk about frost weathering. This is a fascinating process that really shows how nature can shape the landscape over time. Essentially, frost weathering occurs when water seeps into cracks in rocks, and then temperatures drop, causing the water to freeze. As it freezes, it expands, about 9%, which puts immense pressure on the surrounding rock. Over repeated cycles of freezing and thawing, this pressure causes the cracks to widen and eventually break apart the rock. What's important to remember here is that this process is most active in environments where temperatures fluctuate around the freezing point regularly, like in mountainous or temperate regions. It's a key form of mechanical weathering because it physically breaks down rocks without changing their chemical composition. Connecting this to the broader theme, frost weathering plays a crucial role in the physical breakdown of rocks, leading to soil formation and shaping the landscape over geological time scales. It's a perfect example of how climate influences geological processes, highlighting the dynamic interaction between weather and Earth's materials. Now let's talk about frost weathering. This process is a key type of physical weathering that happens in cold climates, especially where temperatures fluctuate around the freezing point. Essentially, water seeps into cracks in rocks, and when the temperature drops, that water freezes and expands. This expansion exerts pressure on the rock, causing the cracks to widen over time. Repeated freeze-thaw cycles are what really drive this process. As the ice melts during warmer periods, water can infiltrate even deeper into the cracks, and then when it freezes again, it pushes the rock apart further. Over many cycles, this can lead to pieces of rock breaking off, kind of like nature's way of slowly chipping away at solid rock surfaces. It's important to highlight that frost weathering is especially significant in mountainous or polar regions where temperature swings are common. This process contributes greatly to the breakdown of rocks in these environments, influencing landscape evolution. So, in the big picture, frost weathering illustrates how climate conditions directly shape geological features over time. It's a perfect example of physical weathering working hand in hand with environmental factors, helping us understand how landscapes change and evolve. Now, let's talk about mineral composition and how it influences weathering. You see, not all minerals are created equal when it comes to resistance. Some minerals are much more durable than others, which affects how rocks break down over time. For example, quartz is known for its resilience. It's highly resistant to both chemical and physical weathering. That's why quartz-rich rocks tend to last longer in the landscape. This concept is important because it helps us understand the stability of different rocks and how landscapes evolve. So, in the bigger picture, mineral resistance plays a key role in shaping the Earth's surface and the processes that drive erosion and soil formation. Now, let's take a closer look at mineral composition and how it influences weathering. As you can see in this diagram, different layers of rock weather at different rates, and this really depends on the minerals that make up each layer. The key idea here is that minerals vary in their resistance to weathering. The layers that are sticking out the most are actually the most resistant to the weathering process. Think of them as the tough, durable parts of the rock that don't break down easily. Conversely, the layers that are more recessed or weathered away are made of minerals that are less resistant, so they wear down faster. This variation in weathering rates based on mineral content helps shape the landscape over time. It's fascinating because it ties directly into the overall theme of how rocks change and break down naturally. So, understanding mineral composition gives us insight into why certain rock formations stand tall while others erode more quickly. Now, let's talk about how crystal growth contributes to the process of mechanical weathering. When rainwater evaporates, it leaves behind a layer of salt inside cracks in rocks. Over time, these salt deposits don't just stay put, they start to grow as crystals. As these salt crystals expand, they essentially wedge themselves into the cracks, exerting pressure on the surrounding rock. This gradual buildup of crystals creates a force that can break the rock apart. So, in a way, the growth of salt crystals acts like a natural wedge, gradually pushing the rock apart until it fractures. This process highlights how chemical and physical weathering can work together to break down rocks over time, which is a key part of our overall understanding of landscape evolution. Now, let's talk about slaking. This process is really fascinating because it explains how rocks respond to seasonal changes. Essentially, during the wet season, rocks absorb water, which causes them to expand slightly. Then, when the dry season arrives, they lose that water and start to dry out. As the clay within the rocks dries, it shrinks, and this shrinking creates cracks. These cracks are important because they help to break the rocks apart over time. So, in a way, slaking contributes to the natural weathering process, gradually breaking down rocks into smaller pieces. This cycle of wetting and drying is a key factor in landscape evolution, especially in regions with distinct wet and dry seasons. It's a perfect example of how environmental conditions directly influence geological processes, connecting to the bigger picture of soil formation and landform development. Let's take a closer look at chemical weathering. Essentially, this is the process where rocks break down or decay due to chemical reactions. Unlike physical weathering, which involves just breaking rocks apart physically, chemical weathering involves changes at the mineral level. It happens when different mineral particles within the rock come into contact with water, acids, or other chemicals. These interactions cause the minerals to decompose or alter their structure, leading to the eventual breakdown of the rock itself. This process is particularly important because it influences soil formation and landscape evolution over time. It's a key part of the overall weathering cycle, working hand in hand with physical weathering to shape our environment. Understanding chemical weathering helps us see how rocks transform and contributes to our broader understanding of geological processes. All right, on this slide, we're looking at the different types of chemical weathering. These processes are key because they help break down rocks through chemical reactions, changing their mineral composition over time. First up is oxidation. This is kind of like rust forming on iron. When minerals containing iron are exposed to oxygen and water, they oxidize, which weakens the rock and causes it to crumble. Next, we have carbonation. This occurs when carbon dioxide from the air or water reacts with minerals like calcium carbonate in rocks, such as limestone. The result is a dissolving process that gradually carves out features like caves and sinkholes. Then there's hydrolysis. This process involves minerals in rocks reacting with slightly acidic water, leading to the formation of new minerals and soluble substances. It's a major factor in the breakdown of silicate rocks, transforming them into clay and other materials. Finally, we have hydration. This is when minerals in the rock absorb water, causing them to expand and weaken. Over time, this expansion contributes significantly to the disintegration of the rock structure. All of these processes are interconnected and play a crucial role in shaping landscapes. They highlight how chemical reactions, driven by environmental factors like water and air, work together to break down rocks, supporting the broader theme of how Earth's surface evolves over time. Now, let's talk about oxidation. Oxidation happens when water and oxygen in the air react with certain materials, especially metals like iron. When this occurs, the oxygen combines with the metal and some of the earth minerals present, leading to the formation of iron oxide. You might know this better as rust. Rust is that flaky, reddish-brown substance that weakens metal structures over time. It's a clear example of how oxidation can cause materials to deteriorate. which is an important concept to keep in mind when we think about material durability and corrosion. Essentially, oxidation is a natural process that highlights the importance of protective measures in engineering and maintenance to prevent damage caused by rusting. Let's talk about carbonation in the context of rock weathering. When carbon dioxide dissolves in moisture, like rainwater, it forms carbonic acid. This weak acid then reacts with minerals in the rock, especially those rich in calcium. The reaction gradually weakens the rock structure, causing it to break down over time. Calcium-rich rocks, such as limestone, are particularly vulnerable because they readily react with carbonic acid. This process is a key example of chemical weathering that shapes many landscapes. Understanding carbonation helps us see how certain rocks deteriorate faster in specific environments, which ties into the broader theme of how different weathering processes influence geological formations. Now let's talk about hydrolysis. Essentially, this is a chemical reaction that happens when rainwater, which contains hydrogen, interacts with minerals in rocks. When rain falls and seeps into the cracks and pores of rocks, the hydrogen in the water reacts with the minerals inside. This isn't just a simple wash-away process. It actually changes the very chemical makeup of those minerals. What happens next is pretty important. These chemical changes weaken the structure of the minerals, making the rock itself more fragile. As a result, the rock becomes more susceptible to other weathering processes, like physical breakdown or further chemical reactions. In the big picture, hydrolysis plays a crucial role in breaking down rocks over time, helping to shape landscapes and contribute to soil formation. It's a key piece of the puzzle when we're understanding how rocks weather and degrade naturally. Now let's talk about hydration and how it affects rocks. Hydration happens when rocks absorb water, and this process causes the minerals within the rocks to expand. As the minerals swell, they generate stress within the rock's structure. Over time, this stress can cause the rock to weaken and eventually break apart. This is a key form of mechanical weathering because the physical changes from water absorption lead to the disintegration of rocks. Hydration is especially important in environments where water is regularly available, and it ties into the bigger picture of how rocks break down naturally over time. Understanding this process helps us see how landscapes evolve and how different weathering mechanisms work together. Now let's talk about biological weathering. This is the process where living organisms actually contribute to breaking down rocks. It might sound surprising, but plants, animals, and even microorganisms play a role in this. For example, when tree roots grow into cracks in rocks, they can exert pressure and cause those cracks to expand. Over time, this can lead to the rock breaking apart. Essentially, biological weathering is a natural way that living things help shape and alter the Earth's surface. It's a key part of the overall weathering process because it interacts with physical and chemical factors to gradually break down rocks into smaller pieces. So, next time you see roots pushing through cracks in a sidewalk or rocks splitting apart in nature, you'll know that biology is actively involved in the weathering process. Now, let's take a closer look at some of the various biological actions that contribute to soil formation. One key process is root wedging, where plant roots grow into cracks in rocks and gradually break them apart as they expand. This is a slow but powerful natural force. Next, we have the role of decaying vegetation and animals. When plants and animals die, their remains decompose and add organic material to the soil, enriching it with nutrients essential for new life. This process is vital for maintaining soil fertility and supporting ecosystems. Animals also play a part through their hoofs, which can physically break down rocks and soil as they move across the landscape. Their movement helps mix soil layers and accelerates weathering. Humans, too, influence soil formation, whether through agriculture, construction, or other activities. Our actions can speed up or sometimes hinder natural processes, shaping the soil profile in various ways. So, in summary, soil formation results from a combination of biological actions: roots breaking rocks, decomposing organic matter, animal movement, and human influence, all working together over time to create the soil we rely on every day. Now let's look at plant action, specifically root wedging. What happens here is quite fascinating. The root of a plant starts to grow into tiny cracks or pores within the rock. As the root elongates and thickens, it exerts pressure on the surrounding rock material. Over time, this consistent pressure causes the crack to widen or deepen. Essentially, the root acts like a natural wedge, gradually breaking apart the rock from within. This process highlights how biological activity contributes to physical weathering. It's a great example of how living organisms and geological processes work hand in hand, gradually shaping and transforming the landscape over time. Remember, this root wedging is a slow but powerful force in the overall process of rock breakdown and soil formation. Now let's turn our attention to plant action, specifically root wedging, which is a fascinating process in geotechnical studies. Root wedging occurs when plant roots grow into cracks and crevices within a soil or rock mass. As the roots expand, they exert pressure on the surrounding material, effectively wedging their way in. Over time, this process can lead to the widening of cracks and, in some cases, even the disintegration of the material. This phenomenon is particularly important when we're considering the stability of slopes or retaining structures in natural environments. Roots can both stabilize a slope by binding soil particles together, but they can also cause destabilization through wedging if they grow into existing weaknesses. Understanding root wedging helps us predict how vegetation impacts soil and rock stability, which is crucial for both erosion control and landslide mitigation. Remember, this process exemplifies the dynamic interaction between biological activity and geological materials, highlighting why plant action isn't just about growth. It's also about how those roots influence the surrounding environment over time. Now let's look at plant action, specifically root wedging. As plants grow larger, their roots also expand and become more forceful. When these roots encounter cracks or weaknesses in rocks, they start to push against the edges. Over time, this continuous pressure causes the roots to penetrate deeper into the rock. Eventually, as the root continues to grow and exert force, it can break the rock apart. This process is a great example of biological weathering in action, where plant growth actively contributes to breaking down geological materials. It highlights how living organisms, like plants, play a vital role in shaping and transforming the landscape over time. So, the key takeaway here is that plant roots don't just grow for stability. They can also be powerful agents of physical change in the environment. Now let's talk about plant action, specifically root wedging, which is a fascinating aspect of how plants interact with their environment. Root wedging occurs when roots grow into cracks and crevices in rocks or soil, exerting pressure as they expand. Over time, this pressure can cause the cracks to widen, and in some cases, even split the rock apart. It's a natural process that shows how plants can contribute to physical weathering. This process is especially important in the context of landscape evolution and soil formation, because roots essentially help break down larger rock masses into smaller, more manageable particles for soil development. It's a slow but powerful force. Plants are not just passive elements of their environment. They actively shape it through mechanisms like root wedging. Connecting this to our overall theme, understanding root wedging helps us appreciate the dynamic role plants play in geological processes. It highlights the importance of biological activity in physical weathering and landscape change over time. So, next time you see a crack in a rock or a boulder with roots poking into it, remember, this is a clear example of how plant action can influence and even accelerate natural processes of erosion and landscape transformation. Now, let's take a closer look at how plant roots actually help break down rocks. Tiny root hairs are constantly seeking out small cracks and pits in the rock surface. These tiny hairs grow into those tiny spaces, applying gentle pressure as they expand. Over time, this process causes the cracks to widen and the rock to break apart gradually. It's a slow but powerful form of weathering that plants facilitate. This interaction between roots and rocks plays a crucial role in soil formation and landscape changes. So, essentially, plants aren't just growing on the surface. They're actively contributing to breaking down the Earth's crust, helping to create the conditions needed for other plants and organisms to thrive. Now, on this slide, we see a fascinating example of how plant roots actually play a crucial role in weathering rocks. In the picture, you can observe a rock that has been split into two parts, and this has happened because of root expansion. Essentially, as roots grow and expand over time, they exert pressure on the surrounding rock. This pressure causes cracks to form and eventually leads to the rock breaking apart. This process is a key part of biological weathering, where living organisms actively contribute to breaking down rocks into smaller particles. It's an important natural mechanism because it helps in soil formation and landscape shaping. What's interesting here is how this ties into the broader theme of our presentation, which is about the interconnectedness of biological and geological processes. Roots don't just stabilize plants, they also actively alter the Earth's surface. So, this example from Harriman State Park in 2005 really highlights the powerful influence of plant roots in shaping the environment. It's a reminder of how living organisms are not just passive inhabitants, but active agents of change in Earth's geology. Now, let's talk about the significance of weathering. Weathering is actually a crucial process in shaping our Earth's surface. It breaks down rocks into smaller particles, which then become the building blocks for soil formation. Without weathering, we wouldn't have the rich soils that support plant life or the landscapes we see around us. It also plays a key role in the rock cycle, gradually transforming rocks from one form to another over time. This process influences everything from the formation of mountains to the creation of valleys. Understanding weathering helps us appreciate how landscapes evolve and how Earth's surface remains dynamic. It's a fundamental part of geology that impacts ecosystems, human activities, and the overall environment. So, in essence, weathering is not just a slow, natural process. It's a vital driver of change on our planet. Weathering is really the planet's way of maintaining balance. Think of it as nature's way of equalizing the processes happening on Earth. When volcanoes erupt and deposit new rock into the atmosphere, that material eventually makes its way back down to the surface through weathering. It's like a cycle. Volcanoes send material up, and weathering pulls it back down. This ongoing process helps regulate the Earth's surface and keeps everything in relative harmony. So, in essence, weathering acts as the planet's natural balancing act, ensuring that no single process dominates and that the Earth's surface remains relatively stable over time. Many of the unique features we see on our Earth actually originate from the weathering of mountain ranges. These processes are fascinating because they help create the diverse landscapes we observe today. Weathering isn't just about breaking down rocks, it's also about shaping the environment in ways that are both scientifically interesting and visually stunning. Importantly, weathering plays a crucial role in the formation of soil. This soil then becomes the foundation for growing our food, supporting agriculture and sustaining life. So, in a way, the weathering of mountains is indirectly responsible for the food we eat every day. Overall, understanding these processes helps us appreciate the interconnectedness of Earth's features and the vital role they play in our ecosystem. Now, let's talk about how weathering actually contributes to the formation of sand on beaches. When rocks are exposed to the elements, like wind, water, and temperature changes, they gradually break down into smaller particles, eventually turning into sand. This natural process is quite important because it provides a vital resource that can be used for construction purposes, such as building materials, or even for creating tourist attractions. Speaking of attractions, weathered rocks don't just serve practical purposes, they also create fascinating sights for visitors. For example, the Kiti Mikayan Seam Hills is a popular tourist spot because of its unique weathered formations. Similarly, the crying stones of Kakimga are famous for their intriguing shapes and the stories they tell. These sites show how weathering not only shapes our environment, but also adds cultural and aesthetic value, making them important for tourism. Overall, weathering plays a dual role here. It provides essential materials like sand that support construction and economic activities, and it also offers natural wonders that attract tourists, enriching our cultural experiences. So, Understanding these processes helps us appreciate both the practical and recreational benefits of our natural environment. As we wrap up our presentation, I want to highlight an important material that forms through the process of weathering: bauxite. Bauxite is actually a product of hydrolysis, specifically from the breakdown of plagioclase feldspars. This process involves chemical reactions where minerals are decomposed by water and acids, leading to the formation of new substances like bauxite. Now, why is bauxite so significant? Well, it's the primary ore we use to produce aluminum. Without it, the aluminum industry as we know it wouldn't exist. So, from weathering processes, which might seem like natural disintegration, we actually get materials with substantial economic value. This connection underscores a broader theme we've been exploring: that weathering isn't just about breaking down rocks. It's also a vital part of Earth's resource cycle, fueling industries and supporting